Good morning and welcome. I will be discussing dynamic programming concepts and tools, which are useful tools for actually speeding up the running time of recursive algorithms in particular. So we would basically be looking at how do we identify problems that are suitable for application of dynamic programming, and what are the steps that you need to go through in order to successfully apply dynamic programming to your algorithm or to actually solving a given problem. In the past, we have discussed, a very useful design concept called divide and conquer, where basically we have a complex problem to solve. We then split this problem into multiple problems, and then solve these sub problems, and at the end combine the solution to form the solution for the complex problem that we actually start with. This has proven to be a very useful tool in the design and analysis of algorithms. But now that we are discussing high performance algorithms or programming, where you basically want to improve or speed up or scale up your algorithm or your program, it is then useful that you have a couple of tools, which includes dynamic programming and other tools that we will be discussing in subsequent lectures. So let's see an example of a problem that will help us to actually motivate dynamic programming. So consider the example of you actually wanting to compute the so-called Fibonacci numbers, right? So these numbers are defined, for example, as we can see here. So what we have is that if n equals to 0 or 1, then the fib of n is equals to n itself. So, but if n is greater than or equals to 2, we have this recurrence expression where the fib of n is the fib of n minus 1 plus fib of n minus 2. We have in the past discussed a couple of practical examples and all that for this particular problem. So for motivating dynamic programming, let's take an example that n equals to 5, as we have illustrated in the recursion tree shown here, right? So what we would like to calculate in this case is the fib of 5. A traditional, naive, and very simple approach to implement this is the recursive program that we have over here, right? So what we have is basically implementing the expression up here in this algorithm, which we call fib of n, right? So now you can see that this algorithm calls itself repeatedly, right? But what really happens when you run the algorithm is what is being illustrated in the recursion tree over here, right? So to calculate fib of 5, the very first step is your algorithm run through all the steps, and then when it gets here, it needs to now calculate fib of 4 and n minus 2, which in this case is a 3, right? So then, for you to get 4 is greater than 1, you will still need to use the same recurrence expression, and then you go on until you reach 0 and 1, right? So what you have is, other than the leaves of this recursion tree, every internal node has 2 operations being performed, and then a summation operation as given in the definition here. But the problem is here. Look at calculating this. Look at a fib of 30, for example. This is calculated twice. The same thing, but done twice, right? Fib of 2, the same thing, but calculated twice. And based on this observation here, what you would see is that when you increase n, say to n above 10 and all that, you will see that this algorithm takes significantly long time to actually run. This you would like to avoid in general, because You don't want to wait a lifetime for you to get the result of a computation as basic as what we actually have here. So the natural way that we can do this is to find mechanisms that will eliminate the need to repeatedly compute the same or solve the same problem, right? So we want to eliminate this, eliminate this, eliminate this, eliminate this, eliminate this. The way to do this is to now use dynamic programming. So let's see what are the tools applicable. So what we have seen in the last slide is a recursive algorithm, or what I could then call a top-down recursion kind of, right? Where you start from the larger problem and you successively progress downwards until you reach the base cases for the particular problem. So the base case for this fib problem is fib of 0 or 1. So when we reach there, then we have reached the leaves of the recursion tree, and this helps us to actually calculate or solve the complex problem. Now, the problem, as we have seen, is the repeated calculations, which we need to avoid. Two ways that are commonly used is either we keep the top-down approach, but then memoize the calculation. So basically, what we will be doing is to now use an additional memory, right? It could be in form of an array, a table, a map, or other data structure that you may actually find useful for the particular problem, such that instead of repeatedly calculating or solving problems, we would instead store result of any calculation in this extra array that we have actually created, for example. Then the next time, or whenever I need to now repeat or recalculate this, I don't need to now recalculate. I basically need to do a lookup into the array, or just search for that particular entry in the array and use it, right? The second approach is the bottom-up approach, where instead of starting from the top, which is the problem, the complex problem that you would like to solve, you would start from the base case for that problem and progressively compute intermediate problems, keeping the results and then fetching them when you need them again, right? In general, these two approaches have been shown to be asymptotically equivalent in terms of the running times, and depending on the programming and the choice of implementation, the bottom-up approach kind of allows us in some cases to reduce the space complexity, or equivalently the memory requirement, right? We will see an example of how this can be done in subsequent slide. But two things to keep in mind: you have a recursive algorithm, your goal is to speed this up. Then what you can do is either to do a top-down approach or a bottom-up dynamic programming approach. So let's see an example. You have a rod, so a given rod of this length, right? And then you know that there are price tags for rods depending on the length of the rod, right? An example is given in the table here, where we're saying we have length in whatever unit. It could be in meters. Let's just take that as an example. And then a 1 meter rod costs, say, $1 US, right? A 10 meters rod on the other end costs $30 US. Now you have this rod of length N. In this example, let's take N equals to 4. So I have a 4 meters rod and I would like to sell it. But how should I sell it? Should I sell it as a whole? Should I break it into 2? Should I divide into 4 and sell, such that I get the maximum revenue from the sale of that rod, right? So what are the number of options? How many ways can I divide this rod of length 4? The options are basically shown down here, right? So what we have is, I could sell the entire rod as it is without splitting. I would get a revenue of 9, right? Because my rod is of length 4. I could cut 1 out of it and leave the rest. I would get, for the 1 meter length and the 30 meter length, I will get $1 and $8 US respectively. right? Progressively, you can see that these are all the options that we have for cutting a 4 meters rod, right? But now for each of them, you can see some numbers which basically indicate the price or the sales price for each part. So if I take the example H, for example, so this one here, what we have is that I would basically get a revenue of 4, which is 1 plus 1 plus 1 plus 1, right? But if I basically leave my rod as a whole and just sell it, I get $9 US. But you can see there's another option. Option C gives me $10 US. So basically, option C is the option which maximize my revenue. Now, how do I apply dynamic programming to solve this problem, right? Now, what we would like to do is to split this rod, then progressively solve it and check for the solution that maximize an optimization problem. So here, what is our optimization problem? As we can see from the illustration here, it is straight to then write the reward, which the revenue, which we would like to get for a rod of length N as the maximum, right, of a rod P, the revenue for selling that rod without cutting. So that would be A in this case. Compared to, for example, if you take B, so you have R1 and R1, 2, and 3, right? That's N minus 1. If you come here, you have R2, N minus 2, right? R3, N minus 1. And then you can progressively or recursively break this down. So we can basically write this as a maximization problem of this form, which we can see that it's easy to see that this reduces to the form that we have here. So for the rod cutting problem, our goal is to apply dynamic programming to solve this optimization problem down here, right? So let's see an algorithm to solve that. Again, we have said earlier on that for the rod cutting problem, we have, for a rod of length 4, we have 8 options, 8 choices of smaller problems or ways to divide the rod and sell it, right? So we can generalize this, in fact, to say that you would have, 2 to the power of N minus 1 ways of cutting a rod of length N. So now we could also represent this operation that is being performed in a recursion tree, similar to what we did for the fib operations as seen here, right? So this recursion tree is for the case where N equals to 4, and then we, progressively indicate the problem. So in the first case, you could take 4 and split it into nothing. So you take 4 and 0, or you take 3 and 1 or 2 and all that. So what you can see is that we have a tree or a recursion tree with 2 to the power of N nodes. So if you count the number of nodes here, you will get 16, right? But there are 8 ways of cutting the rod. So what is then the running time, right? So what is the running time of an algorithm to solve the rod cutting problem, a recursive algorithm? So what we can see is that at every node in the root, so if we start from the root node, we have a constant operation, which is the summation operation, before you start splitting into 2 smaller problems, to be this. And then we take the summation from j equals to 1 to 0 up until N minus 1, right, of T of j, where T of j is the time it takes to operate on each node. It is actually straight to solve this either using the master's theorem or the substitution method, and show that this in fact reduces to a running time of the order of big O of 2 to the power of N, which is an exponential running time in N, which we would always want to actually avoid because it does not scale at all. Even for fairly small problem size, you may have to wait unbelievably long for you to solve that problem. Here we have a Python implementation of the algorithm rod cutting for those of you who might want to try your hand on this I would recommend that you reproduce this algorithm and then use the example in the last slide to actually confirm that indeed the maximum revenue is actually 10 and that the algorithm works. So this is a recursive algorithm, then, which is unbelievably slow. We would like to speed this up using dynamic programming. See that we do memoized where we still do the recursion, but keep results, or we do a bottom-up approach. An example of a bottom-up program for the rod cutting problem is shown here again in Python, right? So what you see is that we create the memory here as R, and then because we are performing a maximization operation, the identity for that problem would be minus infinity. So I would initialize my result as a minus infinity here, and then I could then put the maximization problem into this and use a loop to search over the entire space that we would like to actually maximize over, right? Which is the number of possible, ways to actually cut the rod. But how long does this algorithm take to run? I will again not go into detailed mathematical derivation of the algorithm, but what you can see here is that we have two nested loops here. One loop going from 1 to n, and another one going from at least 1 to n. This should be n plus 1, in fact. So this means that the asymptotic complexity of this algorithm will be of the order of n to the power of 2. So we have basically now reduced an algorithm with exponential time to a polynomial time algorithm, right? But at what expense have we achieved this reduction? So what you can see here is that for the recursive algorithm, we don't need this additional array that we have created here, right? So that means that the space complexity for the recursive algorithm, it's not dependent on the problem size. So we have a constant requirement for memory. But in the case of this bottom-up cut rod, we have order of n, right? But the time has been decreased from 2 to the power of n to n squared, which is a very huge advantage here. I would like to point out here that there are alternative ways to actually implement this algorithm such that you also have constant space requirement. Okay, now we have seen an example of applying dynamic programming to solving the rod cutting problem. As with other algorithmic endeavors, it is often necessary that we have a way to analyze or, the running time and all that of our algorithm. For the example, for the recursive algorithm, we could rely on the recursion tree. But when we now have dynamic programming having a number of problems, what we need to do is to create what is often called a sub-problem graph. Where basically what we do is to now create a directed graph, G, with the nodes in that graph, which is V, being a set of all problems. For the example of n equals to 4 rod cutting problem, we would have this as the sub-problem graph. And what you see here is we have a total of 5 problems, problems. So the problem itself and 4 problems here, and depending on how they interact. So the edges basically indicate for each sub-problem, which other sub-problem do you rely on, right? So at 4, we will need every other sub-problem, the same for the other nodes and all that. So this gives us the what do we call it? The sub-problem graph for the rod cutting problem. What we can then see from here is that we can basically calculate the work and the depth of this algorithm by inspecting the sub-problem, right? So the running time here is basically of the order of the number of nodes plus the number of edges in this problem graph. So this problem graph can in fact be generalized to any type of problem that we would like to solve using dynamic programming. So far, I would like to just mention here that since in the last few slides, we have basically discussed how to, calculate the optimal solution. For example, in the case of the rod cutting problem, we have just basically tried to calculate the maximum revenue I can get for selling a particular length of rod. But we have not really returned or also find the, the decisions or the choices leading to that optimal solution. What are the possible combinations of, of cuts, rod cuts that I need to make to get the maximum reward? So the idea here is to actually show that in many applications, we are not only interested in the overall maximized costs or reward or what have you, but also the decisions or the choices made. And that is what is being done in the example algorithm or modified algorithm for the rod cutting problem here. So to sum up, if you have a problem P and you would like to apply dynamic programming, what you need to do is to determine a set of all possible sub-problems that you need to solve in order for you to achieve a solution for P, right? And then you then need to find a subset of this set, right? Such that when you compute a given one, you would only need results from smaller ones or sub-problems having a lower rank in the set of the order of the problem as shown here. And then you solve all these sub-problem that you have selected, study solution, and based on that, you can then calculate the solution to P itself. So this is just a summary of the things that we have been discussing. You divide into problem for each sub-problem, you solve it. So which in sometimes means you need to decide for this particular problem, what are the optimal choices, kind of, right? And then all these collected together constitute what is referred to as the decision, right? And then at the end, what you would like to get is an optimal policy, a way to actually go from each step to the globally optimal solution you are interested in, right? But before you apply dynamic programming into solving a problem, there are two basic things that you will need to look out for. The first one is optimal substructure. So which basically indicate that for dynamic programming to be applicable, then we should be able to construct an optimal solution from the solution of the smaller problems, or sometimes it's actually stated that a recursive algorithm will need to repeatedly compute a number of the problems to be able to solve that problem. If this is actually seen in the problem, then we can say that we can apply dynamic programming. But optimal substructure alone is not enough, because there is also other type of algorithm or programming framework, which is called greedy, that can be applied for problems that has the optimal substructure property, right? So then we also need to confirm that our problem has another property which is called overlapping problem, right? So which means that for you to have you need to have a set of smaller sub-problems which ordinarily will be reused several times, as we saw in the case of the fib or the rod cutting problem. Then you would say that you have overlapping problem. So if a particular problem P has these two properties, then you are safe to basically assume that the most useful way out of solving that problem is dynamic programming, and then you can then apply the concepts discussed earlier. Let's see a more practical example. You would like to take a trip from a particular town to another town, right? And your goal is to minimize the costs of the trip, the overall cost of the trip. There are several things that would impact the cost, right? Your choice of route, which places do you make your stopovers, which hotels do you choose, and all that, right? You are driving a car, and then as such, you also need to take into account the travel cost, which will be impacted by the distance between successive stops. Now, how do you choose which routes to take, which hotels to stop, which towns to stay, and all that, such that you get the minimum cost possible for your trip? Let's see how to actually solve that step by step. So, in terms of an optimization problem for dynamic programming, we could write the cost minimization problem in this form here. We would like to minimize the total hotel cost plus petrol cost, right? Now, this is a recursive approach where, for example, you're at a previous town, now you are moving to this town. So it means that whatever route you take or the amount you spend on fuel for a particular stage depends on the costs that you have actually accumulated from the previous stage. And that is what we have as the last term of this expression here, right? So you want to minimize this, where all the indices and all that are defined as we have here. So let's see an example here where we have basically said you are traveling from Aalborg to Copenhagen in Denmark, and then you would like to stop in a number of towns in between, right? So we represent the possible choices as stages. So the first stage, which is the 0th stage, is you in Aalborg living here, and as such at this stage you don't have any cost, right? Now at the first stage, you have a number of places to stop. Each place differs in the cost of travel, which is indicated here, and the hotel cost, which is what we have up here, right? So which one should you take? And the same is applicable to from stage 1 to stage 2 until you reach your destination. And while at the destination, you still have to choose from a number of hotels to actually stay. Now, let's take it stage by stage. So what we will ideally do in dynamic programming is to then, start from the base case and say, okay, the one sub problem is traveling from stage 0 to stage 1. The second sub problem is traveling from stage 1 to stage 2, and so on until we reach the end here, right? So now the base case is here. So we will start from the base case in a bottom-up approach and keep going like this. So the bottom-up algorithm, the operation of it is illustrated here. So in stage 1, which is the first problem, going from stage 0 to stage 1, is illustrated here, where for each option or stop option here, you have the total cost as the cost of a petrol and hotel, and then you can basically indicate which one is the minimum from that. Then for the second stage, which is you now moving from 1 to 2, you could do the same thing. So the costs at stage 1, which are the ones here, plus the, petrol cost plus hotel cost and all that is calculated. And then basically the cost here is just the one that minimizes the minimum among all the options, and which place gives the minimum, which place do you leave from to get the minimum cost traveling to any of the 2 points in stage 2 are given here. The same is done for the next stage and the fourth stage. So that then in the last part of the program, now that we have solved all the problems, then we now need to construct a solution from the solved sub-problem. So what we will do is to backtrack, track the solutions backwards, right? Starting from the last until we reach the first. And that we can basically do, if you look at 4 here, right? You have a number of choices to do, which is 3 times 4, which is 12. But for each destination point, you have a minimum cost, right? And the corresponding origin. So now you will now compare all the minimum cost and select one of them. So if we choose this I, so it means I to J, right? So that is the solution we will have in stage 4, I to j. So now the starting point for solution 4 is I. So essentially, we will then go into the solution for the next stage, which is the third stage, and check where do we have the minimum cost with a destination point equals to I, which is this one. So we would take E as part of our solution. And as such, we have now added a new entry into the solution. Same will be repeated for stage 2, where we take E as a destination point and check which minimum costs, where do we start from such that we get the minimum cost to E, which is B, and then we do the same thing for stage 1 to obtain the overall solution. So it may also be of interest to you to try to now analyze, based on these steps, what is the second best solution? Right. I would recommend that you try this exercise just to get into the discussion on dynamic programming. And then now we would like to summarize the discussion so far. So what we have seen is that in traditional sequential algorithm, you could implement iteratively or recursively. Recursive algorithms are sometimes very, very useful, but for certain problems, they may become unbearably complex in terms of the running time. In fact, many recursive algorithms will have running time that is asymptotically exponential. So you don't want to wait for that. Dynamic programming provides you with a way to actually do that. And basically what you do is to do something similar to what you will do with divide and conquer framework, where you break a complex problem into a set of sub-problems. You store the solution to any problem. You solve each sub-problem successively, store the solution either in an array, a map, a table, or any other data structure. Then, which means that instead of recalculating the solution to a sub-problem, you basically just do a lookup, just search for it, right? Then, this approach is used in several places. For example, you have a graph, you would like to find all pair of shortest paths. You want to solve an optimization problem, as we have seen. This is also used in flight control and robotics control and all that. Another very useful example, especially for computer scientists and engineers, is the maximization of usage of the central processing unit and all that, right? So what do I need to check before applying dynamic programming to my problem? Two things that you need to bear in mind: optimal substructure, or the idea of having overlapping problems. If you have questions, feel free to drop them in the comments, and I will try to clarify. Yeah, thank you.